Notacon.
Excellent. Okay. Thank you all for coming to the talk. This is DEFJAM to Cutlass 1 year after. My name is Todd MacDermid. This is Jack Lloyd, and this is Kathy Wang. John Schweitzer is also one of the principal members of the project, but sadly he is in Florida this week and cannot make it. Cutlass is something that actually started out last year at Notacon. It was founded kind of as a community project. Some jump roping girls kind of tied us into doing something, and the idea was that at the time we were calling it distributed encrypted file journaling and messaging, and we got together a bunch of people at the con and we talked about the design, and it was more of a freewheeling kind of oh, let's just sit together and talk about what this project needs and what it doesn't need. And we can go in that direction this year. We have a full hour's worth of prepared material, but if you guys are interested at any point in going off on some tangent, really the whole point of this talk, whoops, no, okay. So we'll get to that in a bit. But the idea is that we're looking for help. And so if you guys are interested in helping out with the project, we would love to have you, and we can make progress with it. We're going to show you what we've done. But as we talked about last year, the primary goals behind Cutlass was it's an encrypted voice over IP, file sharing, and text messaging application. The idea is that those are the core things besides web surfing that people do on their day-to-day lives. I've got a bunch of friends that I hang out on the net with, and we talk to each other, we send files back and forth, and currently it's pretty much all going over in the clear. And the idea is they're not tinfoil hat people, but I am a tinfoil hat person, and I really would like to bring the rest of the populace inside the encrypted envelope, so to speak. Now, we need it to be easy to use because my friends are lazy and they're not going to put up with any kind of annoying crap in order to use encryption. It pretty much has to be seamless and not actually there. And it's also got to run on Windows. Currently, it runs only on Linux, but it's been designed to be portable. We actually have run the library, and it's on Solaris. It's on a few other platforms. We're not using any funky Linux-only mechanisms within it, so hopefully it should be pretty easy to port. It's got to be secure by default. There should not be an option to make it easier to turn the encryption off. It ought to, if it's not working with the encryption on, it's not working. SSH is actually the model that we're shooting for. SSH has more or less replaced Telnet in most shops today because it's really easy to use. It's not that much more difficult to use than Telnet, and you don't even need to know much about the encryption that's happening behind the scenes. Because we are a small project, we're not already the size of a Kazaa or a Nutella, we don't want it to be a valueless product unless there's already a million other people using the product. We want it to be useful by a small set of people, so that you can do it. If it's only just you and your 5 buddies, it's still useful to use. While I want it to be easy to use for the general populace, that means that some of the more tinfoil hat things, key verification, the web of trust that GPG has, for example, isn't going to be on by default, where you have to sit there and pay a lot of attention to who your keying material has come on. But I want it to be there so that if you do care about that kind of thing, that it is easy to check and you can go back and make it more secure without too much difficulty. And I also wanted to avoid the dependence on central servers. If you look at Skype, for example, there's one central logon server. After you've authenticated, it all goes out to various subnodes, and all your traffic gets routed around via those subnodes. But you do have that one central server initially. That's going to lead to some interesting things with CALIA, for example. There's going to be some legal impacts of that. If you've got a central server that people can target, then it may become your responsibility to retain information about transactions that are going on. And I wanted to avoid that. It is not a strong anonymity system. It is not trying to go out and eat the lunch of Tor, for example. If you have a strong anonymity system, that usually has a huge usability impact in my experience. And I couldn't figure out any ways to design around that per se. So where anonymity is in conflict with usability, usability wins. We also didn't restrict ourselves to using standard protocols that are already out there. So, for example, we're not using RTP for our voice. We're not using TCP for our file transfer. That has had an impact over the past year because we've had to replicate some functionality. And I've had second thoughts at times, but that was the decision we've made. We forged ahead with it. It's pretty much working at this point. And we wanted it to be useful without a complete meshing of all the nodes. We didn't need there to be one global namespace. So what we've done to date is we've got audio working. We've got key exchange. All the crypto stuff is working. We've got a decent housekeeping system that will detect if connections are up live or not, and clean up after itself without memory leaking and all that fun stuff. It's got a text messaging system. It's a file transfer system. We've got support for directories in the library, but we don't actually have it integrated into the UI yet. And that's going to be a really key step, so that when you come online, right now you need to know the host that your friend is at, and you need to try and connect there and see if he's up or not. That's obviously not going to scale. It's a test framework at this point. We're debugging the code. The directory server support is in there. It's not activated yet. It will be shortly. So we're going to demo this now to show you what we've got. Jack, do you want to take it or?
No.
Go ahead. And by default, we have a passphrase protecting your private key. And I've already talked to Kathy today, so I've already got her information in here. And I've increased the font size. Normally under default font sizes it looks sane, and we need to clean up the GTK a little bit. But this is it, effectively. You can add contacts, you can edit contacts, you can remove contacts. I've already got a contact, so I'll just connect to Kathy. And at this point, we've got a text chat window. So, and Kathy wants to do an audio chat with me already. And so Kathy is actually using a different client.
Kathy is actually using a different client than we are.
And we're into the audio loop. But we can chat back and forth at this point.
But we can chat back and forth at this point via audio.
And I'm going to stop that because it works.
I'm going to stop that.
You've seen it works, and that's going to get really annoying if it just continues on that audio loop. But Kathy said hell to me. Hiya. And we can have this text chat. I can send her files if I like. We've got the pull file requirement, and I apologize. We've got divvied up into UI components and the fundamental behind-the-scene library, and the GUI is still a little bit unstable. I do want to show you that it does actually work behind the scenes, so I'm going to start up Text Cutlass real quick. Text Cutlass. Oh, you don't have file transfer enabled, do you?
Well, I just transferred a file earlier. Over to
You sent it to me, but you're not receiving.
Okay.
Text Cutlass by default will not receive files. You need to include the -F flag. So, what's a good file to send you? All right. Yeah, I lost the buffer.
So would you like me to send you a file?
No, I'm. Oh yeah, actually you do need to send me a file because I'm not receiving at this point, or you're not receiving. Oh, we need to connect.
Oh, you
What?
disconnected?
Yeah, I did. 92.168.69.118. Okay, so send me a file.
I just did.
No, you weren't.
Let's
We
do
weren't
it
connected
again.
yet. Okay, so I got a file. It comes, it asks me what I want to save it as. And lo and behold, it shows up. So that's file transfer. We've got it working in the library. The GUI still needs a little hammering out.
What we've done in the past with this particular demo.
What we've done in the past with this particular demo is that I usually sit in the NOC, and you know, that way I'm remotely connected to this host, and I can talk through audio, and I can send files, and you know, that kind of stuff. It's really pretty neat. So today we were having a little trouble setting things up, so that's why I'm sitting here instead of in the next room. But just imagine that I'm over there.
So I'm glad you did show up, and we do need help, and we don't need just help in coding, because we've got some good coders on the team. If you do want to code, we've definitely got areas that need help coding, and it's been so much a grab what you find interesting kind of project, and then people will pick up the pieces that aren't interesting and clean them up later. But if you've got testing abilities, if you want to find bugs for us, if you've got design suggestions for the GUI, usability, things like that, we would love to hear from you, because ultimately we want this software to be usable by the vast audience of the world at large, but you guys, the core security community, we expect will probably be the evangelists, because most people, if they look at this versus TeamSpeak or this versus Skype, they're not going to care as much about the security. So it's probably going to grow from within you, and so we would like to target you guys initially. So the purpose of this presentation is not just to demo the software, because we're already done with that, but we're going to try and give you information that would be useful if you would like to help out with the project. We're going to cover the protocol, how that works, how the cryptographic structure works, the internals of the program, the API, because as I've mentioned, it's a library, and then we've got 2 clients currently that are written to that, GTK Cutlass and Text Cutlass. If someone else would like to write a different client, that would be great. We've got a test suite that we currently run that tests the library and what the documentation is. We've been trying to document this project so that anyone could step in, download the tarball, and be helpful in a fairly short amount of time. So to cover the basics of the protocol, it's UDP based, and that's because we've got that audio component in it. And if we go TCP based, you end up, of course, obviously with the problem of you lose a packet and then you've got latency for the rest of whenever. 2 + 2, 4. The answer comes back. And so with UDP, it's easy to drop packets on the floor. Now, why didn't we go with UDP for voice and TCP for other things? Partially because it's easier to punch through firewalls that way. We can replicate TCP functionality within UDP, and we'll talk about how we do that in a little bit. And partially to help defeat traffic analysis measures. Once we get this to where we want it to be, we would like it so that you can add in chaffing packets and the like, so that you don't necessarily will be able to tell if a person is chatting over audio or sending a file. Are you guys familiar with Tarzan? It's an interesting project. It's a peer-to-peer. It's an anonymity network. But one of the ideas they've got is they've got the idea of constant data streams, and it's constant streams of nothing going over. And when you want to actually send data, you remove some of the nothing and you add in the data. But no matter whether you're sending or not, the data stream looks consistent all the way. There have been other people that have implemented it. Tarzan was the first time I'd heard of that. It's not in the Cutlass protocol right now. If you use the library, you will be able to do traffic analysis on it, but the protocol supports that. So that's where we're driving that eventually. That's what we mean when we say extendable and paranoia. We can do transfers of messages to individuals. We can do it to groups, and we run everything over this UDP protocol. This is the core of it. Because it's per packet, we can't do some kind of chain block cipher stream. We're actually doing something that's closer to WEP, but we tried not to screw it up. So we've got this nonce up here, and currently the default nonce size is 16 bytes. And we've got HMAC at the back. The reason these are variable is because it depends on what ciphers you're actually negotiating, and we'll get into that in the crypto section. You have the packet length field, which is kind of interesting for a UDP packet because the length field is obvious. It's the size of the packet. Except in our case, it's not necessarily, because you could pad the packet out with junk at the end. If the packet is padded out with junk at the end, this length is the length that you're paying attention to, not the length of the datagram that came in off the wire. Then we have packet types. Channel IDs, we have UDP channels that run within that allow you to transfer multiple files at the same time and have it be able to sort it out. And then we've got that type-specific data, which depends on the type. These are not all of the Cutlass packet types. If you do want all the Cutlass packet types, it is documented in the protocol.txt document. But these are probably the keys. We've got the most important packet types. We've got key exchange packets, ping pong packets just for liveness checks, connection information packets. So if you want to change your permissions, for example, yes, I accept files, no, I don't accept files, you'll send out information request and response about those kinds of things. Audio packets, and then we've got a reliable transport layer, which is where the text messages and the files go over. Connection information packets, it's capability flags and your nickname. Capability flags are things like can accept audio, can accept files, those kinds of things. The audio, we're using Speaks as a codec behind it, and so it's a really simple sequence number, and then it's the Speaks data. We just pour it in after that. If you get packets out of sequence, you drop the earlier ones, because we weren't doing that, and we were getting some really interesting effects. I thought Speaks handled that by itself, but it doesn't. The reliable transport layer is probably the area that we've put the most time into. I remember reading a rule of programming that said, "Thou shalt not attempt to replicate TCP's functionality," because it's a lot of work. And it is a lot of work, which is why it's where we spent most of our time. If you've got a transport packet, you have a sub-transport type within that packet. And those are things like initialization, the initialization ACK packet, data send, data request, and channel reset. That's a pretty close analogy to what you've got in TCP without the urge flag in there. But it's not window-based. We'll get into that in a second. Currently, we support 3 different types of transports. It would be really easy to add a 4th transport if you wanted. Currently, it's messages and direct requests are memory-backed transports, meaning you write it into a memory buffer. And then if you do a file transfer, it just writes it onto the disk. If you wanted to add another thing, something else that used transport, it's really easy. We don't have like a sockets abstraction layer in there, but it would be pretty easy to go through and add that type in. Now, I mentioned it's not window-based. It's not, start sending me the data, and when you receive the data, it will fill in from the front of the buffer. We actually have the concept of gaps. So let's say you have a 4,500 byte gap. You've got a directory request, and it's going to be 4,500 bytes large. What happens is the remote side will actually start advertising, saying, "I'm missing bytes 0 through 4,500. Please help me out and fill those in." And so the sending side will then pick frames and will send them in. So we've got here bytes 0 to 1,000 will show up. Maybe we'll lose a packet. We lose 1,000 to 2,000, and then 2,000 to 3,000 show up. So at this point, you've got 2 gaps in here. You've got gaps from 1,000 to 2,000 and gaps from 3,000 to 4,500. And so you would advertise that back to the remote side saying, "I'm missing these parts. Could you please fill those in?" And so it'll fill in 1,000 to 2,000. And 4,500. Actually, what I just illustrated there was probably an out-of-sequence arrival. This arrived, that arrived, this arrived out of sequence. When you advertise a new gap, the number of gaps increases. It will actually switch ends to allow any out-of-sequence packets to show up. And so it will start writing in from the back end. So at that point, we only have 1 gap left, 3,500 to 4,000, and that gets filled in. So we can actually do some, well, here are the rate limiting rules that we've got right now. If you get a request in for a gap, you immediately send a response out with some data in response to that gap. If we get a successful request-response pair, meaning we've got a new request that came in without an increase in the number of gaps, and the actual amount of data that his requesting has shrunk, it'll increase the rate by 1 packet per second. So we can spin up faster if we've got a fast connection. And so we'll periodically send packets that we didn't get a request for that. We'll continue writing off the end because we assume that it's still getting there. So we don't need to have an ACK for each packet. We're not latency bound by that, which would be really stupid. If the number of gaps increases, if we get fragments, something has arrived out of order or we dropped a packet, drop the unsolicited packet rate. And that is our back off so that we're not slamming the channel. Some stats that we've got, and this is over a local link. SCP takes 45 seconds to copy a 34 megabyte file. It took Cutlass 53 seconds. So we're in the ballpark of TCP, which we haven't done that much tuning yet, so I'm not surprised that we're not being quite as fast. We're also a little bit slower to spin up than TCP currently, and we're quicker to fall back. So if we were doing simultaneous connections, we were actually using 75% of the bandwidth. SCP was eating it, and Cutlass stabilized at about 25% of the bandwidth. So we're a little less aggressive than TCP, which is probably a good thing because we don't want to gain a reputation as a horrific protocol that will eat all your bandwidth and nothing else will work. And when you're trying to play in the same space as TCP is, that's pretty important. Now, because we're this UDP-based protocol, we've got some advantages that TCP doesn't normally have. We're unrestricted by window size, so you don't have. So if on a very high latency link, if they ever get the interplanetary internet running, we wouldn't have to worry necessarily about we can only write out to the window size in terms of bytes, and then we've got to wait for at least some of that data to get acknowledged. We can continue writing out there. We're only going to write slowly. It will be a slow spin up, but we would continue writing and we would be able to send those unsolicited packets and fill the pipe that way. The key advantage here is that it's easy to turn into arbitrary BitTorrent chunks. Currently, BitTorrent picks a block size, for example, 1 megabyte, and then it will go out and ask for 1 megabyte chunks from various and sundry people. With this, because we're advertising gaps and the gaps are in bytes, we can ask for arbitrary byte ranges from multiple people. So we could get multiple transfers going, and as gaps fill in from those other people, we can advertise different gaps to all those transfers simultaneously. If we just maintain state about what gaps are in our files, we have no losses whatsoever, and it would be really easy to start from a halted transfer again. And the unrestricted by window size would give us the high latency performance, but we haven't actually tested that yet, so take that with a huge grain of salt. Theoretically, it should work, I think. Are there any questions about the protocols or transport layer that we've created? All right. Well, Jack is our crypto master, so I'm going to turn it over to him for the crypto.
So we were, starting out this project, and we realized that we were going to have to develop our own UDP-based crypto. So we, sat down and decided to take some time, go over what attackers we were concerned with and how we were going to stop them. And then I'll give an overview of the handshaking protocol itself. Todd showed you earlier the packet layout. These sections, and it's somewhat confusing because the shaded out areas are the actual unencrypted going in the clear. Everything else that you see here is encrypted and hopefully not visible to anyone sniffing on the wire. Some potential attackers, there's probably others, but ISPs sometimes get curious, board mail admins, etc. Cops, competitors, any various and sundry TLAs.
You gotta watch out for KFC, man.
I mean, you look at that kernel. You can't trust that guy. Some of the many possible attacks, but these are the ones that we have included kind of explicit countermeasures for. Key recovery, just any sort of attack, say stealing your machine and just grabbing it there, or anything of that nature. Man-in-the-middle attacks or active attacks in general, replaying packets, modifying them, trying to inject new ones, things like that. Traffic analysis, just looking at everything that's out there, and direct cryptanalysis. Some of the many ways to recover keys. The RIP Act, I don't know. I don't suppose anyone here is from the UK, but okay, well then you're all safe unless you visit the UK. But the RIP Act, if you're not familiar with it, is basically a law in the UK that says if the government wants, you will hand over your keys or you'll go to jail. And if you disclose that your keys were taken by the government, you get an extra 5 years tacked on your sentence. So, good fun. There's two main features in the Cutlass crypto protocol to help at least mitigate these attacks. The private keys, as you saw in the demo, are protected with passwords. So if you choose a good one, you know, if someone just steals your laptop, maybe they won't be able to get the key.
I should point out that in the interest of usability, we've made the passwords optional. There's a warning box that says, you know, do you really want to be a fool and not protect your key with a password? But it is optional.
And actually, probably one of the most important features in the protocol is the Diffie Hellman key exchange, because I mean, I'll go over the details later, but essentially we do a key exchange with keys that we generate just for that transaction. We generate a key and then we throw them away. So even if someone is to compromise your long-term keys, they won't be able to read a past conversation. They'd only be able to read future ones that you made encrypted using that key. Mostly readable. Some potential ways to do man-in-the-middle or more active attacks. They're not trivial. I mean, it would seem to be difficult to do active attacks on every single SSL transaction being done all over the world. So it's going to be more of a targeted per user or per group sort of, we're interested in these people, or, someone trying to mess with you specifically rather than just doing it for fun. Actually, Todd, do you want to talk about CentreTrack? Because that was a pretty interesting story.
I used to work at UUNet, and one of the things that we had running in there was a project called CentreTrack, and the idea was for denial of service mitigation. The idea was that you could propagate a route out for one specific IP address that actually went to a GRE tunnel that would go down to the UUNet lab. And you could then analyze all the packets going to that one particular IP address, and they'd all be coming through your one router. If they came in on any gateway in your network, they'd all end up going to this one router in your lab. You could slice them, dice them, do what you want before you then push them out to the exit gateway on that side, which went down to the customer. And that was for denial of service mitigation. The idea was that if someone was getting flooded, you'd set up a CentreTrack tunnel, send it down to your lab, be able to figure out what kinds of things were happening in the packets, is there anything we could filter on specifically, and then put those filters in place. So when you hear people say that, it's not really possible to track all traffic on the internet, we weren't getting all traffic on the internet, we were just getting all traffic through UUNet to one IP. But that's a good chunk of the internet that would be talking to that one IP. So the technologies, and there are public papers on this that you can go read about if you do just a Google search on CentreTrack. It is possible to route individual IPs of interest through central locations. At the time, you could detect it via traceroute, and they were working on how to have that avoid showing up. But
conspiracy theories abound.
Yes.
Countermeasures to a man-in-the-middle attack. We do more or less the SSH style. Presumably, you've all used SSH, where you connect to a machine. If you've already got that key, then great, you have already known somehow who this person is. And if you've never talked to them before, then just accept whatever key that you're given, which is vulnerable to a man-in-the-middle attack. Someone can splice a new key in at that point, but they can only do it once, presuming you keep the key around. The audio component provides a fairly easy way of verifying keys. We're already talking, I know your voice, we can exchange key fingerprints over that, and it would be possible, but it seems a little difficult for someone to do a man-in-the-middle attack, then replicate your voice. Possible, but this actually should have been in anti-goals.
Yeah, it's true.
But we're not interested in a X509. As lucrative as that might be to become the next VeriSign, I don't think that's very much fun or is going to happen. So try to keep things small and decentralized.
That is completely anti-usability to try and reinvent
Yes.
that kind of key sign.
Traffic analysis, I presume you're all familiar with the idea. There's been some pretty interesting research papers within the last few years that you can get a lot of information just by looking at how often people talk and who they talk to. Cutlass is not going for full prevention of traffic analysis. Generally speaking, if I'm talking to Todd, someone will be able to tell.
By
But
default.
yes, by default, it will be blatantly obvious because there will be packets beaming back and forth between us. A feature that's kind of in the hopefully near future but not implemented yet is
protocol spec.
Yes, is tunneling traffic. So I could route traffic to Todd through Kathy, so it would seem as if I was talking to Kathy and Kathy was talking to Todd, or possibly that we were talking through Kathy. And that will be useful both to help, stop traffic analysis a little bit, but more importantly for going over NAT, especially in the case where you've got two users both behind a NAT that they can't modify to forward ports or anything. Chaffing and padding help limit the disclosure from the size of packets and how often they're sent. For example, I think it's 50 packets a second for voice. And so if you're talking and you're seeing 50 packets a second going back and forth in each direction, it's pretty obvious that people are talking. With chaffing and padding, you can basically randomize that to some extent, but as Tarzan, again.
Yeah, exactly.
So, and direct cryptanalysis, which I was actually thinking primarily in the sense of, well, hey, we've got this machine that breaks AES, or something of that nature, but in general, any sort of direct cryptanalytic attack on the cryptanalytic attack on the protocol itself. Replay attacks, IV collisions, which is what screwed up WEP, if I recall correctly, or weaknesses in the actual crypto itself, in the algorithms. As I mentioned, it's a Diffie-Hellman key exchange. All strong algorithms with a hopefully known good implementation. There's no export ciphers, no weak algorithms included for backwards compatibility. The 128-bit initialization vectors mean that the odds of an IV collision are exceedingly small, 1 in 2 to the 64. Well, no. Very small. It's too early to do math. Different keys in each direction, which is actually a pretty important one, that when we first did the protocol, Todd was asking why, and I thought for a second, I can't think of a good reason, but something is telling me, yes, you want this is standard issues thing. And the real problem is, if you're using the same key in each direction, someone can take a packet that you've sent to someone else and turn around and send it back at you, and when you check the authentication code, it will match because it was generated with the same key that you're expecting. This is the provisional 5-year plan for where the crypto is going. I've been kind of constrained into that area at this point. But like I said at the beginning, there was no good UDP-based crypto system. DTLS is working its way through the ITF right now, which is basically TLS 1.1 modified just enough to be usable over UDP. A very common request is support for OpenPGP. People want to reuse their webs of trust, and that is also, actually, I think that may be an RFC now, but for OpenPGP authentication through TLS. So the idea is eventually you will be able to plug your OpenPGP key in, and it will just work with no separate key system. But that will take a while because I code very slowly. Okay, well, if there's any questions about the crypto, in which case I'll hand it back to Todd for internals.
So we're going to talk about, if you did want to help out with the project, we're going to go over the internals of the project. If you guys have no interest in coding and you would like to talk about a different aspect, we can clearly do that. We're pretty familiar with most of the aspects of the project. But if you're all tired and haven't had enough coffee yet, I'm going into internals. So we have two primary core data structures that run around inside. The one that you'll see passed everywhere is the Cutlass handle. It's the Cutlass T-type. This contains information such as your local private keys. It contains all your local configuration information. It contains the sockets that are open so that it can read across, it selects across all the sockets. It's got a hash table that contains all the connections and mutices protecting that hash table. It's got a hash table containing all your directory entries and mutices protecting those as well. There's a lot of locking. It's a multi-threaded model, which I'm going to get into in a little bit. The other data structure that you're going to see thrown around everywhere is the connection handle. So every connection that you have with a remote person is going to have one of these supporting it. It contains the session keys that you've negotiated with that one particular person, any capabilities that the remote side has. If they've got a unique socket, if you connected to them rather than them connecting to you, it lets you know what socket that is. It's got all the transport buffers, so the state, if you've got channels, multiple channels of data coming in, it's got data for each one of those channels, what gaps you currently have in there. I mean, there's a lot of stuff in here. Actually, each one of these is probably a 30-element struct, and I'm just covering the high points. But that's fundamentally what's in those structures. Now, Cutlass actually internally is a multi-threaded beast. The three core threads are the listener thread, the housekeeping thread, and the user interface thread. Now, the user interface thread is what you yourself would be writing if you were writing to the Cutlass API. The listener thread just sits there and it blocks in a select all day. So it selects across open sockets, waits for packets to come in, and as packets come in appropriately, it'll dispatch them out to wherever they need to go. The housekeeping thread is keeping track of time. So it will sit there and block and sleep. And it will modify, it's actually a U-sleep, and it'll modify the U-sleep time, and every time it goes through that next sleep, it tries to figure out, well, when's the next event going to be coming up? I'm going to sleep for that long. So things like, by default, if a connection is inactive for 60 seconds, tear it down, get rid of it. If a connection is inactive for 30 seconds, send them a ping. You'd send a ping out, the pong would come back in, the listener thread would come in, lock the connection table, lock that particular connection, update the connection to say it's alive now, and it would go on. The UI thread is what you write, so if you've got actual user input, that needs to go out to the remote side, you would do that, and there are a few API calls that I'm going to cover that you do that through. Now, there are a couple other threads that pop up sometimes, and this is the audio threads. If you've actually got an audio connection or multiple audio connections open, you've got an audio reader and an audio writer thread that are pulling data off the microphone and sending it, and then waiting for packets to come in off the listener thread. They'd get put in the connection's audio buffer. The audio writer thread would wake up, see that it's got audio in the buffer, write it out to the audio device. We're using right now the OSS audio model, which if you've got ALSA support in, also provides OSS handles as well, so you can just use that easily. When we're porting to Windows, that's obviously going to be one of the big things. It's all modular, so it should swap out fairly easily, but that's what we're using for audio right now. We also have these things called action handlers. And action handlers are the way that the listener thread and the housekeeping thread will let the UI thread effectively know that something interesting has happened. Cutlass, as I've mentioned, is currently into a library, and we've got 2 clients right now. And you've got to register an action handling function. So if you wanted to write a client, here's what you would do. You would call Cutlass init. That gives you back a Cutlass handle. Then you'd modify that Cutlass handle, which I'm going to get into. You'd register all of your action handlers, which I'm going to get into. You'd call Cutlass start. Cutlass start actually kicks off all the threads and things run at that point. Now just go handle your user input. If you've got user input, you want to send a file, call Cutlass send file. If you want to send a message, Cutlass send message. And then when you're done, you call Cutlass shut down all. So it's actually a pretty simple flow. You could write a really minimal client in, gosh, probably 100 lines of code in C. It's not hard. Here are some of the highlights of the calls that you would call to modify default values. Most of these are actually optional. So Cutlass set port, there's a default that comes out of the handle when you get it initially. Nickname is set to blank string by default. If you want to change your permissions, default permissions are just receive text messages. But if you want to receive files, if you want to receive audio, you'd call the Cutlass set permissions. The ones that are not optional down here are the Cutlass load private key, which if you've got a key file, it will load it in, and you are supposed to pass a passphrase function, so you get your own passphrase to load private key. If you don't have a private key file, we'd recommend that you call generate RSA key, and that will have that loaded for you. Now, I mentioned the action handlers prior. These are kicked out by the internal threads to you, and they actually are a separate thread that forks off so that the listener thread isn't blocking, waiting for you to deal with that specific action. And they happen on events that the UI might possibly want to know about. So if a user connects to you, an action handler gets kicked off containing data saying, hey, there's this user that has connected to you. If a user offers you a file, if a file transfer is completed. There's a complete list of action handlers that there's probably 25 or 30 of them, and they're all documented in the action handler guide, which is in the docs directory. Now, if there are 25, 30 action handlers and you've got to register them, how do you end up with a 100-line client? Every action handler is optional. You don't have to handle any action. By default, if you don't handle an action, just nothing will happen. It won't kick out an action handler. So if you don't care if a user file transfer has completed, don't register the file complete action handler, and it won't let you know. There won't be any kind of UI message, and that'll be fine. The only action handler thing that is registered by default is the internal message, so things like errors and stuff like that. By default, there's an action handler in there that just prints them out to standard error. If you want to deal with them in a different way, though, you can re-register that action, and that way you don't have to have your messages going out to standard error. You can have them pop up in a little text box, for example. And there's an opaque structure that gets passed to every action handler function that you can extract information. So what connection is this, action associated with? What's the file name? What's the hash of that file? Things like that. I've got pretty much all the useful information that I think you would need in an action handler coming out of there. Read the API docs and see if I'm missing anything, if there's useful information that I haven't actually given you yet. We've also got a test suite that if you're modifying the library, before you send any patches, I would highly recommend that you run the test suite across it first. It does things like check the handshaking, make sure it can talk to itself. It'll send itself, 100 messages ranging from 1 byte to 60,000 bytes. It'll send files back and forth across itself. It won't test its own audio thing. So if you're messing around in the audio subsystem, there is no automated audio tests yet. But if you're making modifications to the library, please run the test suite before you send me patches. It does not also test APIs. There is no API test suite. So if you're making changes to Text Cutlass or GTK Cutlass, you kind of have to just test that on your own. Documentation that we've got, we have a separate /docs directory, and we've got the action handler guide, which is a list of all available action handlers and what information comes what you should be expecting when you register that action handler. It's a pretty consistent API, but sometimes if you get an error action, it may or may not have a remote connection associated with it. So you shouldn't depend on there being remote connection information associated with that error. The API.txt is effectively running you through, except in greater detail, the past 10 slides, telling you, this is the flow that you would need to do in order to write a useful Cutlass client. The goals are just our stated goals, and so if you're ever curious as to think, well, should I make this design decision or not, that would be where you would pull that out of. And these are all open for edits, so if you want to suggest changes, we are open to them. The internals, we've got some locking policies so that we don't end up in a deadlock condition ever, for example. So, for example, thou shalt never lock connections and then go lock the big handle, the Cutlass handle, because everything generally goes lock the Cutlass handle, then lock the connections. So this is those kinds of policies that we've got in there, and it also describes the threads and how they interact with each other. And then we've got the protocol.txt, which is the network level. So if you wanted to not use the library of Cutlass, but instead, rewrite something that spoke Cutlass protocol, you would look at the protocol.txt document. Are there any questions at this point? Okay. So you've seen what we've got done so far, and in some ways we've done the hard bits. We've recreated a reliable transport layer, we've got audio working, but in other ways we've done the easy bits, because now we come to the interesting design decisions about how do the directory servers interact with the users to make sure that we end up with a highly usable experience. Cutlass right now is functional. It gets data from point A to point B over an encrypted channel, but it's not very usable. It's not highly user-friendly, and we really do want this to be software for the average person. So to handle groups properly, we need to handle other OSs, clients for other OSs, because all my friends use Windows, which I'm working on, but they still all use, well, not all of my friends use Windows, but some of my friends use Windows, and I'd like to talk to them. We need to activate the directory code in the clients. The directory code is in there now. We need to do the connection forwarding. That's going to be important for, automatic NAT detection, for example. If you've got two guys behind NAT, with UDP, actually, you have the ability, if you can set your source and destination port, which we can, you can punch holes through your NAT firewall unless it's randomly assigning ports on the outside. So we'd want to try that, and then if that doesn't work, automatically fall back to try and forward a connection through a friendly, someone that has that activated, that will allow connection forwarding. And we'd like that to happen seamlessly, so you never need to know, hey, I've got to forward my connection through these 3 hops in order to get to my final destination. So we've got that auto detection code to do. And then once we've got all that, easy stuff done, well, we'll put a video codec in there and, make a game plugin, and everything will be blissful and wonderful. So in some senses, we've done the core, we've done the guts, we've done the hard stuff, but we've got interesting times ahead. Talking about what we have not yet done, Cutlass groups, the grouping code isn't currently done. Yes, in the back. Oh, 5 minutes. Okay. Actually, that's pretty good timing. Grouping code doesn't currently exist. Right now, it's just connections between individual point-to-points. If you want to have 3 people all connected together, they can all chat as a group, but they're all, if you're doing chats to messages to everybody, it's everybody you're connected to. There's no way of picking subsets of those people. So that's the grouping code. We anticipate that the groups will either be authenticated or unauthenticated. The authentication types will be password or key whitelist, effectively, that you allow these people in and not those people. You can either advertise groups on directory servers or not advertise them on directory servers, and no one will know about them. And that code is in the directory server code. However, when we do group communication, we will not have a central group server a la Silk. Silk, you guys know Silk? Encrypted IRC chat. It's not bad, but there is a central point. It's the central IRC server, and everybody shares that IRC server key. If the IRC server were to be compromised, all applications going through that would be owned effectively. The way that we want to do Cutlass is it will still be point-to-point communications. What you'll just have is a group owner who will tell all group members, hey, here's who's in the group. And then at that point, you'll know who to send your messages to when you're sending it to that group. Those will be the super ops. The super ops will have there will be a private group key associated with each individual group. If you do give out super ops, you're actually sharing that private group key so that you can effectively sign, statements of here's who's in the group. You can't revoke that. There is no effect of, revocation of super ops. You could also delegate trust via regular ops. So that would just be a super op attesting that you should listen to this guy's decisions. He would not get a copy of the private group key. That authority could be revoked, and that would allow for your regular op wars that you normally have fun with on IRC channels. The only problem is that if the super op went away, he would not be able to designate new regular ops, and the group could fall apart. So you might want to distribute your superops, distribute that group key. Directory servers, the code is in there, has been added over the past couple months. Anyone can be a directory server by default. We don't want to have any kind of central directory structure. But currently you can store registered users so that you can all decide to meet. You guys play, BattleNet kinds of things? You meet on, Azeroth East, for example. So you'd pick a directory server that you'd go meet up on. One of the things that we're not doing right now is we're not trying to make this a central file repository. We're trying to just make this a list of users, and then presumably you could go out and there would be some functionality so that you could search files within those lists of users. Connection forwarding we're still working on, and I've talked about that a little bit. And so really we would like you to help out, and there are a couple ways that you can help out. One way that you can help out is by downloading the software and giving us feedback, and that would be very much appreciated. We have a mailing list. It's actually an encrypted mailing list using PGP. So when you send a mail to Cutlass Subscribe, it will actually send back the group key, the list key in the response, and then in your, yes, this was not a spoofed email, that your actual activation message, if you include your private key, or not your private key, sorry, whoa, it's a little early for me. If you include your public PGP key, you will be on the list and all messages will be encrypted to you. So it's kind of a neat software, and it gives you a pain that current encryption technologies have. If you do need help running that, I am more than happy to help out. I realize that not everyone's got their encrypted email set up flawlessly yet. The other thing you could do is we actually have t-shirts that we are selling at this con. They're brand new. And they are $15. And if you would buy one of those, that would be spectacular as well. So at that point, are there any questions? Well, I thank you very much. And I'll be here.